Okay, there's a problem that we just did at the whiteboard by, basically paper and pencil. I did talk about using a calculator also, but right now let's just talk about looking at the problem in a graphical way, right? So it says, for example, suppose we have a 10,000 acre forest and it can support 1,000 deer. That's a carrying capacity. Now, what does that mean? It means the forest can support 1,000 deer. So if you were to put 500 deer there, you'd expect the population to grow to 1,000 and level off. Now, if you put more than 1,000 there, like let's say 1,500, the forest couldn't support it, so the deer would decline and they'd level off at 1,000, right? It goes on and says, assume the population follows the logistic model. All right, the logistic model is what we just covered over here, and we went through the derivation of that. Hope you could follow that. It also says the K is going to be 0.4 per year. Find the deer population if the initial beginning population of the deer is 100. All right, then it gets how long will it take the population to reach 500? So what I want to do is use software. I'm going to pull Grapher into view over here now. And I just want to turn some things off here. I want to turn a bunch of stuff off. And the first thing I want to do is talk about using software. I mean, we've been doing direction field for a while, but I noticed that they got, y and t. So it's really y is a function of t, but I'm going to say y is a function of x just to make it easier for me. So I still have this vector where the x is taken the place of t there, all right? So, dx dx is 1, and then again I say dy dx. Again, remember I'm taking x to be t now. What's that going to be? Well, I'm going to go over and, whoops, sorry about that. I'm using a different mouse over here. So let me go back over that. And looking at this thing over logistic model, sorry about that. My mouse is really kind of sketchy here. So let me just pull inside over here. The logistic model is this dy dt, is what we're doing over here. So it's dy dx equals k. K was 0.4, y, and then it's going to be parentheses 1 minus y. And A is the carrying capacity, and the carrying capacity is 1,000. Right, then I plot that direction field, and I got this over here. All right, that's a direction field there. Now I want to point out, I'm looking at certain things in the direction field, and you may wonder what those things are. One thing is there's a horizontal line over here. My suspicion is it's happening at y equals 0, and over here this would be y is 1,000. Now the population up here is greater than 1,000. You'd expect it to be coming down. And I notice those curves are coming down over here. Over here, it looks like the curves are coming up and leveling off. Here, it makes no sense to me. It's a negative population, right? So what I want to do is plot this over here. That's y equals 0. I'm also going to plot y to be 1,000. I'm seeing that over there, all right? So again, between a 0 and 1,000 for y, I'm expecting the population to rise up to that. If the population is above 1,000, I'm expecting to fall down to 1,000. All right, let me erase that over there. Okay, the next thing I want to talk about is the solution that I found. And let's go back to the work over here. And we did this at the whiteboard. The solution I found was this over here. So I want to graph that in. I want to graph the solution in. And the solution we found, and again, through the work, we found 1,000, 1 plus 9 e to the minus 0.4 t. And I get this curve over here. All right, I'm going to turn that off now. And what I want to do is talk about getting Grapher to actually plot it out. And what I'm plotting out, well, we're going to just type in the differential equation now, which is going to be dy dt. In this case, it's dy dx equals 0.4 y, and then it's going to be 1 minus y over the carrying capacity, which is 100. With the initial condition, let me go back over that with you, was at time t equals 0. That means they put 1,000 deer into the property, and they said it's 0 is 100 deer, all right, 100 deer at time 0. And then I notice it, look over here, I got a picture of that. Now let's look at our solution as it compares to that. Now I don't see any difference between the two. Now it could be they're not, there's no difference between the two, but I'm going to say I want to go back and talk about the algorithms being used over here. So I want to go back to Inspector. Let me pull it up for you. And again, for some reason they're defaulting to Runge Kutta. I guess it's better than Euler. I don't know. But I'm going to go back to Euler method because that's the method we've kind of described. And I want to talk about, if I took the step size to be 0.5. Remember, you got to refresh it, and I'll do that over there. I notice the fit right now, I do see some separation over here. All right, but anyway, yeah, you can keep going different step sizes. And let me just go back to 0, 1. All right, let me refresh it again. The other thing I want to point out is they asked me to figure out at what time would the population reach 500. So what I did is I determined it would take about 5.5 years to do that. So what I did, let me go to the point over here. I'm going to open it up. I'm going to edit the point and show you what I put down over here. And again, the point that I'm putting down is when we saw that it's roughly 5.5 years. That's the x value, I'm making it t. And I said 500, and we plotted the point, and we get the point over here. All right. What I want to do now is play around with the initial condition. I'm going to start to turn things off, including a solution to it. And I'm going to use, the direction field. But I want to talk about initial conditions changing. Like, let's say I started off with, I don't know, 200 deer. And again, what am I expecting to do? I'm expecting a population to grow up to 1,000 again. All right. And that's not 20. I want to do 200. Oops, 200. Okay. I see that. All right, I'm seeing it grown back up to 1,000. Now, let's say I did something which I think would be rather cool to do, is to put 2,000 deer. In other words, crowd them. Crowd them in the area. Throw 2,000 deer. You're going to expect problems. There'll be limited resources, limited water, other animals taking them out, whatever. All right, it's going to decrease to 1,000, the carrying capacity. And I do see that, by the way. Now, I want to point out if you put 1,100 deer there, whoops, 1,100. Again, I'm expecting there's going to be a decrease, right? Now, if you put, I don't know, let's put 800 deer there. And you get an idea how fast these curves are changing for me. What am I seeing? Growth of population go up to 1,000. And that's something important. You start to use software to visualize, all right, to visualize what's happening over here. Again, we can do the exact solutions. We can get a slope field drawn, and we can start coming up with a differential equation, just type it in, and put initial conditions that we want to change. Where they are. Put 1,000 there. What happens when I put 1,000 in? It's flat. Absolutely flat, by the way. Let's say I put 0 in there. What's happening though? They're absolutely flat. Nothing's happening over there. Now, if you go below 0, I want to point out, it's kind of ridiculous to do that. But like you say, minus 100 deer, it makes no sense at all, by the way. But if you do that, what's happening over here, it just looks crazy to me. It looks like, oh, it's getting worse and worse over time, like less and less deer. It can't be negative deer. I hope you realize there's some restrictions over here. Again, 50 deer, let's see what happens. I think you're seeing what's happening over here. Population slowly growing, all of a sudden it kicks up as more indoor deer. But it levels up at 1,000, right? Logistic model. Thank you.